So hello, everybody. This is Robert Franke from LICAT in Rostock, and I welcome you to the fourth event of the Sustainable Chemistry Lecture Series. And this time again, we have two excellent speakers. It's my pleasure to welcome Anja Mudring from Stockholm University, who will show us how to use ionic liquids as transformative tools in material synthesis. And our second guest is Johan Martens from the Catholic University of Leuven, who will give us insights into production, storage, and transportation of solar hydrogen. Before we start with the scientific program, I would like to announce the next SCLS event. So we will meet again on the 20th of May 2021 at 4 p.m. And our guests will be Xiaodong Zhu from Stockholm University and Ian Clay from ICIQ in Spain, and we will hear about advanced transmission electron microscopy techniques for developing novel materials for sustainable chemistry. And the second talk will be about carbon dioxide as carbon-1 resource and catalytic upgrading. You see in the middle of the slide, you see a link. This you can also find at the UChem's website in the calendar. I'm looking forward to meet you all again there, hopefully. All right, so I would like to thank UChem's and KVCV, the Royal Flemish Chemical Society, for supporting our lecture series. And a particular thanks goes to Thomas Franken from KVCV for his tremendous technical support. And a little remark on the discussion, so feel free to post your questions during the talk in the Q&A section or into the chat. Now I'd like to hand over to Adam, who will introduce our first speaker.
Yeah, thank you, Robert, for this introduction, and welcome all of you for today's meeting. It's my pleasure to to invite and to present to you our first speaker, my colleague Anja Mudring from SU. And I have here a short CV about her, which I would start with. So Anja Verena Mudring was born in Germany and obtained her chemistry degree in 1995 from the University of Bonn. Afterwards, she went to the south, to Stuttgart, to the Max Planck Institute for Solid-State Research, where she completed in 2001 her PhD degree on solid-state chemistry with Professor Martin Jansen. Then she spent a 2-year postdoc with John Corbett at Iowa State in the US, before she returned to Germany as a Liebig Fellow to the University of Cologne in Germany. She finished there in 3 years her habilitation in 2006, and was immediately appointed as tenured associate professor to the Ruhr-Universität Bochum, where she stayed until 2013, when she actually returned back to Iowa State, but this time as full professor in material science and engineering. She stayed there until 2017, and then she went to Sweden to join the Department of Materials and Environmental Chemistry of Stockholm University as full professor and head of the Physical Materials Chemistry section. Her research is centered at green chemistry, inorganic chemistry, and solid-state chemistry. She is the founding director of the Stockholm University Center for Circular and Sustainable Systems, and she has also been a visiting professor in Genova, Italy, at Orléans, France, and she has also been an adjunct professor at the University of Alabama in the US, and is currently an honorary professor at the University of KwaZulu-Natal in South Africa. Anja is also very active in the scientific community. For instance, she is the associate editor of ACS Sustainable Chemistry and Engineering, the same for Crystal Growth and Design, and she is also the editor-in-chief of Green Chemistry Letters and Reviews. She has won many prizes and fellowships, I think over 13, and she has got more than over 20 awards. And according to your CV, they are coming more up all the time. I will mention here, for time reasons, only a few, because otherwise the time would kind of go out. So for instance, she received the ERC starting grant and the ERC proof of concept grant. In Sweden, she received the Wallenberg grant, and in 2017, the Göran Gustafsson Prize in Chemistry. And this prize was sent to her directly by His Excellency King Carl Gustaf XVI of Sweden. Recently, she also got the Willem Investigator Award. Regarding her research, the motto is theory with practice, understanding fundamental structure property relationships with the aim to design new materials for energy-related applications. Today, she is here with us, and she will talk about using ionic liquids as transformative tools in material synthesis. With this, I'm very happy to welcome you, Anja, to join us here. We are looking forward to your talk, and the floor is yours.
Thank you, Adam. And it's really a pleasure to talk to you. Thank you, Shube, Robert, and Adam for putting this lecture series together, giving me the opportunity to speak to you. And I watched a little bit the people coming in, and it kind of is mainly reflective of my career. Bernd Krebs, I mean, just one of the heroes of my youth as a professor in chemistry is attending. I see people like Lukas May, who did a bachelor thesis with me back in Bochum, the current group, my current colleagues. So it's really amazing to see the names coming up and to meet you in those times virtually, unfortunately. And I hope that we make it through the pandemic and can meet soon again, all in person, and really discuss science, because that's something we are all excited about. And I will now try to share my screen and take you on a scientific journey. And Bernd Krebs knows that, of course, I started out as a solid state chemist, doing high temperature synthesis, later on synthesis in liquid ammonia. And when you're a solid state chemist and you're using fluxes, ionic liquids are not that far away, although ionic liquids have most been used so far by people in, well, they've been explored as electrolytes in batteries historically, and people in organic chemistry. And I remember in my organic lab class that I always was frustrated when I ended up with something that didn't want to crystallize. And that's what we call nowadays an ionic liquid. But I really would like to show you how we can use those materials that have been around really for a very long time and look at them and see that they have a huge potential, transformative potential, I would even like to say, in material synthesis. And let me try. Now we have the same. I just jokingly mentioned that we had a problem. I had a problem with advancing slides, and we just tried it and it worked, and it did not. So I will stop sharing this screen and pull up the presentation again to get it working. I don't know.
It's the so-called demonstrator effect.
That is something. Okay, let's start it new and probably do it like this. Share screen again. I mean, after a year of online teaching, you would expect us to be better in this. Okay, but now it works. Good. So what are those ionic liquids? And I don't know whether all of you are familiar with that. Many might be. So ionic liquids, as I said, they're nothing else than salts, like the common rock salt, table salt that we know. But in contrast to table and rock salt that has a melting point of a little over 800 degrees of centigrade, the ionic liquids we are interested in are liquid at room temperature. And the easy way to, or design concept to make an ionic liquid is simply to reduce the electrostatic forces. So take the sodium ion and make something that is large, make a large cation. Well, when you look at large cation in the periodic table that are not too highly charged because you want to get down with the electrostatic interactions, you end up with cesium. Not so good, but organic chemistry offers us a wide variety of large cations that we can explore for ionic liquids. And the same we can do with anions. And when you pair a large cation with a large anion, you reduce the electrostatic forces, and many times you end up with a salt that is liquid at room temperature. A colleague, the now deceased Ken Seddon, has mentioned that he believes that a chemist can imagine up to 10 to the power of 18 different cation-anion combinations that give rise to an ionic liquid. So this is really a big playground, and you can do a lot of modifications both with the cation and anion, and each of those are a new ionic liquid with its own set of properties. And that can be the melting point, the viscosity, but also when you think as a chemist, the chemical reactivity. This now liquid has different properties with respect to solubility of salts, molecular compounds and gases, its miscibility with other solvents. And that's why people have coined ionic liquids designer solvents. It's certainly a very big statement, but it really finds its origin in the high tunability of ionic liquids. And now when we think of materials, nanomaterials come immediately into our mind as something where the chemist, and not the material scientist, but the chemist really can contribute with its knowledge. And ionic liquids, well, they are charged. And the beauty of ionic liquids are as soon as you generate a nanoparticle in an ionic liquid, it finds itself in a charged surrounding. So we believe that ionic liquids can stabilize nanoparticles, both electrostatically, but also when you think of the big cations and anions, sterically. So they attach to the surface and they immediately shield the particles. And on the right lower bottom, you see an ionic liquid and a golden nanoparticle in that ionic liquid. And with TEM, we have directly imaged in the TEM the particle in the ionic liquid itself. Of course, you have to have colleagues that are brave enough to put a liquid into a TEM, very expensive machine. The good thing is many of them have a really small vapor pressure so that you can handle them. And this was one that we tested before we did that image in Bochum with colleagues from material science there. But as now that the particle is surrounded by this ionic liquid that attaches to the surface, that also gives the possibility to tune the material that forms in your ionic liquid. And here just some brief examples. So the left SEM images all show zinc oxide prepared chemically from the acetate and a base, sodium hydroxide, in the respective ionic liquid. And you see that depending on the cation of the ionic liquid, for example, the upper left is the butyl methyl imidazolium with trifluoride. We're using, you get nanorods that are fairly large. When you exchange the anion for the thiocyanate, you see you end up with much, much smaller, but still nanorods. If you extend now the alkyl chain on the cation, the imidazolium cation, you see you end up with nanospheres. So by the choice of the ionic liquid, it's possible to tune the morphology. And the effect of the ionic liquid is really very distinct. On the right side, you see nickel oxide that we prepared by a similar reaction route in an ionic liquid, and you see that we obtain nanosheets. When we leave out the ionic liquid, you see that we get small round-shaped particles. So that there's this really distinct effect. And by a smart choice of the cation and anion, you can tune the size and the morphology of your material. But still, it's extremely challenging to understand what's really going on. And that's where we dedicate also much of our research to investigate what are the critical interactions between the ionic liquid and the particle that lead to the respective size and morphology of the materials we are forming. That the particles really are shielded by the ionic liquid becomes also apparent when you look. So on the left, you see one single image in high resolution mode, image in the TEM. But when you take a step back and the larger view, you see that on the upper right image, you see in the same particles swimming in the sea of ionic liquids. And they really, in 2 dimensions, they make a closed packing. And the distance between 2 particles can be associated with the radii of the cations, in that case, because they are the larger ones, of the ionic liquid. So that's something very interesting to know. And that also, when you think of structural hierarchies, and one dream is of building up photonic structures using this design concept of the ionic liquid and the surface control. So indeed, I hope with those first slides, I managed to convince you that ionic liquids really have a tremendous potential when it comes to functional materials, particularly to nanomaterials, where the size and dimensionality and agglomeration matter. Our group, and that is something that I share with Johan, we briefly discussed before, so Johan, our second speaker, that what really fascinates us about being a scientist. I always joke that I never grew up, that I can play around and be creative, but also we can generate ideas to address the challenges of society. And that is what my group has been doing over the last years. So we have been working in the field of nanocatalysts for water splitting, energy conversion, phosphorus for energy efficient light sources, photocatalysts for depollution, and also thermoelectric materials for waste heat capturing. So sustainability is a big challenge for our society, and we chemists can make really great contributions in that with the science we're doing. And one simple image, when I have to explain it, kind of when people ask me, what is the topic that the whole group, and I see many of my students have joined now, is they all work on different topics, but there's one unifying thing, and that is that we want to make smart materials for energy applications. So look just at this old car. It might resemble a good old German Trabi, maybe, which was not very environmentally friendly. But now we all would like to, if we drive a car, to have means of transportation that are much greener. So we could think of fueling our cars with hydrogen, or make electronic cars, have solar cells for light harvesting, take the waste heat generated by the car, for example, from the exhaust, to transform that to electric energy to power the car electronics, which becomes more and more important. So there are a lot of those things, and that ties back to what we are actually doing. And we do that with the help of ionic liquids, not because we believe ionic liquids themselves are green, but they can contribute to making something green. So with the nanocatalyst, I already showed you that it's the size and dimensionality we can easily tune. The other aspect would be photocatalysts for water splitting or for wastewater treatment. A big class of materials that can efficiently split water and also decompose organics in wastewater are, for example, the simple perovskites. Interestingly, when you look at the performance of the different surface facets of such a perovskite, you see that the different crystallographic facets have different efficiency with respect to water splitting, hydrogen generation, or when you imagine a large organic molecule that needs to attach to the surface and then gets degraded. So depending on the application, although you're using the same material, it's desirable to have different surface facets exposed. And here ionic liquids are really smart materials because they attach to the surface. So depending on what kind of ionic liquid you use and what the interactions look like, you get one of the facets preferentially expressed. So That's a big plus of ionic liquids in the synthesis. The other is, and that's now the upper right quadrant, energy conversion phosphorus, CFLs. And I will go into that a bit deeper later. But there are many materials that we have in the light bulbs around us. And the problem is that many of them are polymorphic. So compounds that have the same composition, like the sodium lanthanum fluoride, but they occur in two different crystal structures. And just one gives you the desired performance, whereas the other arrangement is not so efficient. So when you produce the material, you want to direct the reaction outcome towards the one polymorph that is beneficial for your application. And again, you can tune that through playing around with the surface terms when you generate the nanoparticle. And that's again determined by what is attaching to the surface. And that determines the activation energy for crystallization, and in the end guides you towards one or the other polymorph. And lastly, coming back to the thermoelectrics, so energy conversion and storage, one concept for thermoelectric materials is, or one prerequisite is, that you want to have a low thermal conductivity because you want to maintain a temperature gradient, but at the same time, you want to have a high electric conductivity. Unfortunately, the two are related and it's hard to separate them. One concept of separating them is through pores and microstructure. So that is, you take the different scattering lengths of your electrons and the phonons in your material, and you make it nanostructured in such a way that the electrons can travel freely, versus the phonon gets scattered at the grain boundaries. And that again, you can control with the ionic liquid, as you can determine both the size of the particles that are forming as well as their aggregation. So here ionic liquids are also extremely powerful. But coming back to our car, I didn't talk about one thing, and that was the front lights. And I want to take you now on to the journey of illumination, because I think this is an excellent example of engineering, and of engineering that kind of ends in a catch-22. You want to do something good, but sometimes good is when you don't think things through, in the end, it cannot be fully good. And that is a problem that we often meet, particularly when we look at sustainable aspects. So something might be an improvement, an immediate improvement, but you have long-term effects or effects you haven't thought about. So that when you look at the whole engineering concept, that it might not be greener than what had been around before. And energy efficient lighting is probably some of them. And you know, mankind always has been excited about light, from the oil lamps that we now probably mostly know from movies. We can put that or quantify that with the luminous efficiency, so 0.3 lumens per watt. The next thing were the lamps that we found 2 centuries ago in our homes. And even there, the gas lamps, we tried to improve them. And we also see what we see today when we have a new lighting device, we always compare it to the generation before. And even 1 century ago, they did that, say, well, you know, you can, when you put a mantle around your gas lamp, you get something that's superior, and it is 10 times better than an ordinary oil lamp. But of course, we are past that, past the gas lamps, which 10 times better, so luminous efficiency of up to 2 lumens per watt. But they are historic. The older ones, like I remember still the incandescent light bulbs that were around. And again, you see about a factor of 10 when it comes to luminous efficiency and the improvement, 10 lumens per watt. The halogen lamps are an improvement, but not that much. And then the next big step, where we again see the factor of 10, were the compact fluorescent lamp, the CFLs. And they are still, when we look at the use in homes, they're the most common replacement today. That's how the market share of the different light bulbs evolved over time. And we can see that the CFLs, most of them were sold between 2014 and 18. They're really held a large market share. And that is where I said engineering solutions that are not sustainable, because the luminous efficiency of a CFL is really good, but it has another problem. And that's when we look closer at the operating principle. So inside the light bulb, what you have is the glass mantle, and the glass mantle is covered with something. And the reason why it's covered is because of the working principle. You have tiny, well, they say it shall not be more than 2 milligrams per light bulb mercury inside. And when you switch on that light bulb, mercury gets evaporated, you bombard it with electrons, you generate a mercury plasma that sends off UV light. The UV light has a wavelength of 254 nanometers. That's something our eye cannot see. So we need to convert that UV light into visible light. And we do that by means of light phosphors that are coated inside the light bulb. So those are the little gray dots that you see on the surface in the scheme I'm showing you. And those materials, nanomaterials, you need because you want to avoid internal light scattering. So you want the light of the light bulb to get out and not be internally scattered. Those nanomaterials are yttrium oxide doped with europium for the red, oxides doped with terbium for the green, and then again with divalent for the blue. And you convert the high energy UV light, shown in gray, into red, green, and blue, which combined together give a white light impression. But you already see here, well, one of the problems, the mercury inside. That's not sustainable. And we see now that many of the light bulbs that we use as replacement of the incandescent light bulbs get thrown away. We see an increased concentration of mercury in our environment. And that is because of improper disposal of those light bulbs. So this is not a good and sustainable solution. And it would be nice to replace the mercury. And that was back in the times in Bochum, when I talked to colleagues at Siemens and Osram. And one idea that got put forward is to replace the mercury inside by something environmentally benign, such as, for example, a noble gas like xenon. And, well, is that possible? Can we do that? We still want to have an energy efficient light bulb. And when you look at this scheme alone, you see, and I try to depict it somewhat graphically, you're converting high energy UV radiation into visible of longer wavelengths. So you're essentially losing a lot of the energy you've put in. Here shaded in red. The worst is for the red photons you're generating. You see, you're putting much more energy inside than you get out with the red light. If you just take the average and say the average of visible light is 550 nanometers, you can estimate that you lose, even with that energy efficient light bulb, 60% of your energy in the conversion process. It's still a lot more efficient than the incandescent light bulb, but by no means really energy efficient. We have to be aware of that. And you can quantify the efficiency of a light bulb that is based on the discharge mechanism like this, that the efficiency of the lamp is the efficiency of the discharge. And then you look at the term that describes the radiation of the discharge, so the UV light, and the conversion into the visible. That's the one that I marked in red. So there we have the 60% loss. That's bad. So what about our idea with the xenon? The problem is that xenon sends out an even shorter, more energy containing UV light, 175 nanometers. So on top of everything, you're losing even more. And that makes this light bulb simply not energy efficient. Unless you start working at the last term in that equation, and that is the number, the quantum yield or quantum efficiency, the number of emitted visible photons per absorbed UV photon. And if you could do the crazy thing of rendering this higher than 100%, so for example, when we go back and look here at this diagram where we have this terrible red light problem, you see how little energy we're getting out compared to the energy that we're putting in. I mean, that should be sufficient to get out 2 red photons, which means a quantum efficiency of 200%, and rendering the whole concept environmentally benign and energy efficient. And those materials are known. Again, we stay with the rare earth. Praseodymium alone can absorb UV light and send out 2 red photons. The process is not very efficient, but you can use a combination of 2 rare earth ions, and that's gadolinium and europium. So you take gadolinium fluoride and you dope it with europium, and then you can excite the gadolinium, which is the host material. So you only need about 1% of europium in the host lattice. You excite the gadolinium, then you have energy migration through the lattice until you hit 1 europium ion that sends out a red photon. Then you de-excite your gadolinium to a lower state because of the energy transfer. It can activate a second europium ion and you get out the second red photon. This process has been first described by Andries Meyering, and he stated that for this process you need high quality single crystals, because he believed that the surface of the particle would lead to radiationless decay. So you would simply take the energy of the excited state, and because the surface is connected to something, you have organic material, for example, on the outside, that would transfer the energy to the organic material, excite OH, NH, CH bond, and that would lead to a radiationless decay. And we were at that time, I honestly have to say, innocent enough just to give it a try and make nanomaterials. The problem is with all this, you have to have a material that is absolutely oxygen-free, because any oxygen in the material opens up a pathway again for radiationless decay. And that's something we don't want to have. The other question is, how do you make fluoride nanoparticles that are absolutely free of oxygen? Well, in the literature you find you take a mixture of the oxides and treat them with HF. That might work in the lab, but in large scale production, that's probably not the smartest idea to do. And then I remembered the words of my colleague from Imperial College, Tom Welton, who said, you know, BF4 minus containing ionic liquids, they are the antichrists of ionic liquids because they are so unstable and release HF, which is a nuisance for transition metal catalyzed organic reactions when you use them as a reaction medium. But here it's exactly what we want to have. So we took this ionic liquid based on BF4, dissolved gadolinium and europium acetate in it, and then treated it in a microwave. 10 minutes, 120 degrees, like your microwave dinner. BF4 decomposes and releases fluoride. And the fluoride immediately reacts with the rare earth ions and gadolinium fluoride doped with europium precipitates, and you obtain it as nanoparticles. To the right, you see in TM image, it looks ugly because now you have something that can release fluoride, and that's not smart to put into a TEM. It's probably a one-time experiment. So when you wash the ionic liquid away, the particles agglomerate, but again, you can redisperse them and you get finely dispersed nanoparticles, which are about 5 nanometers in diameter. The question is that I sometimes get, well, you use a BF4 minus ionic liquids. You have to make at least the BF3. Is really your way when you think in a systems way better? Well, the BF3 industrially gets made from boron oxide, and you treat calcium fluoride with sulfuric acid. It's still not a green synthesis, it never will be, but it's a lot better than treating anything with HF. So in that context, this reaction is really good and green. And now you can do the acyl-methyl chemistry of the ionic liquid chemist. So you start playing around with the cations and anions. BF4 releases fluoride, PF6 does the same. What about other cations? The first one I showed has an OH group, which can undergo hydrogen bonding. What about if we make something totally hydrophobic that cannot, and big, cannot interact with the particle surface? Or something that is still hydrophobic, doesn't contain an OH group, but is a little smaller, or something that has a pi system that can interact with the particle surface. And we studied all the different combinations in this microwave reaction to make the gadolinium fluoride, and then measured the quantum yields. And we were really happy that one of the experiments gave us a quantum yield close to 200%. So that is really close to the theoretical limit. We were totally excited. There were others where the quantum yields weren't that great. And I still remember we had at that time, Chantal and Johanna, who worked with me at that time. We were in Hamburg at the Hasi lab at the VOV station during night. The results came in and we just wondered what was going on there, because we had studied the materials before. We had taken powder patterns, we had looked at the TM images, and we couldn't fit. They all look clean, but why do you end up where you have always same particle size with different quantum yields? Well, and here the polymorphism comes in. The lanthanide fluorides are dimorphic. So you have the trigonal tisonide type shown on the left, and the orthogonal yttrium trifluoride as two potential structure types. The local environment for the rare earth is the same, and that's why when we did our initial spectroscopic studies, we didn't see much, because with optical spectroscopy, you look at the first coordination shell, and that is similar. But the interatomic distance between the rare earth centers shaded in gray, they are different. And since the whole concept of quantum cutting, so getting to a material that has 200% quantum yield, relies on energy exchange between two rare earth cations, the interatomic distance is quite critical. So when we came home, we looked a little closer at the powder patterns to identify what kind of polymorph we got. And indeed, we found that the material that has the superior quantum yield almost exclusively featured the trigonal tisonide type, and then we made, by simply heating, the orthorhombic yttrium trifluoride material, and there you don't observe the effect at all. So that was something that people had not observed before, and that just showed the importance of the polymorph for the whole story. So we learned the lesson. We were really happy. But there was, I had explained the interatomic distance. So we were happy by that time. people from industry were not so happy because they told us, well, 10 years before, this inside really would have been cool and we would have produced your material. But now we've moved on to LEDs. What can you do for us there? Still, LEDs use rare earth phosphorus, so we felt that our lessons learned probably do not need to go completely to waste. And we looked a little more at how LEDs work. The really cheap ones, you might have noticed, when you take, they all look like, now you can buy the retrofitted, so that's on the lower right shown, where you see a light bulb in this plastic dome that diffuses the light, because that's one problem that LEDs have. They have quite focused light sources. And when you want to illuminate a room, it's not nice to have spotlights. So you put it in a diffuser globe, and the first ones that came out, and you still can buy them, you might see particularly when you look from the side, you detect that in fact inside there are different LEDs that emit in different colors, for example, in blue, green, and red. And that's not nice because, again, it's not truly white light. And you have the problem, additionally, that the red, green, and blue LED over time degrade differently. So the color impression of your light bulb is changing. And that is something that you can electronically compensate for, but you still would need 3 different driving circuits for your LED light bulb. So that's not good. So it would be better to have an all-in-one phosphor, which is not that simple, because now we have to have 3 emitting rare earth ions, like you have in the CFL. You saw there we had the 3 different phosphors, the blue, the green, the red, and you combine them. If you now combine all 3 ions in one host lattice, you have energy transfer mechanisms between them. So it requires some sort to get the right concentrations and to get the right rare earth ions. When it comes to synthesis, it's rather simple, because we can use the approach we had before with the microwave irradiation in the ionic liquid. You take europium for the red, you take terbium for the green, and thulium for the blue. Take the proper amounts, irradiate, and you get something that emits in nice white light. And really, depending on the concentration of the rare earth ions, you can hit exactly the white light spot. So that's good. But still, you have to play around with 3 different ions. That's a bit complicated. It might actually be a lot easier to use the concept that many LEDs use right now, where you have a blue light emitting LED chip covered with a phosphor that contains cerium, which gets activated by the blue light and emits yellow light. So combine yellow and blue to make white. And you can do that by taking dysprosium and thulium, same reaction. So I see it starts getting boring. And you can again hit the white spot. But what is also quite nice, you can play a bit around with the excitation energies and tune the light into something that is more bluish or something that is more yellowish. And when you talk to psychologists that particularly focus on making people in a work environment work more efficiently, one thing is when we see light that is slightly bluish, that activates certain regions in our brain, and we also feel a little more stressed and uncomfortable, but we are more efficient when it comes to work. Whereas when we have something more yellowish, that makes us much more relaxed. So in the evening, when we come home and we, have studied and worked, we want to relax. We want to have the more yellow light during work. The people that employ us want that we see more blue light. And with that phosphor, you kind of can tune it with the same light bulb, which really makes it interesting, just through tuning the excitation wavelengths. But again, LEDs, is it where we really stand? No, Another idea would be quantum dots, so really go beyond what we have now. We can do that again with ionic liquids. The charm is we can use a top-down synthetic technique. Since many of them don't have vapor pressure, you can vaporize material in them. And again, depending on the ionic liquid, you can determine the size. That's really nice, but that might really not be the future, particularly thinking of that cadmium sulfide and selenide are really nice quantum dots, and they are not green materials. So we would like to go more to flexible, nice room light illumination that can also allow for new illumination and design concepts. And believe me, since I've moved here to the Nordic country, I really can see why so much thought is given to the design of light sources. And that's where organic light emitting diodes come into play, OLEDs. They might, with respect to efficiency and brightness, not be really comparable with LEDs. But in contrast to LEDs, you can think of design concepts like this. You could think of wallpaper that illuminates. You can have really very aesthetic illumination that is still energy efficient. And you can buy the first of such OLEDs from IKEA. I just have to show. Interestingly, it came out in Sweden first and in the Nordic countries, and there's still some countries where you cannot get them. And it apparently is that only in the northern countries people would buy such things, and those in the southern country, that there is simply no market for that. But OLEDs, I mean, they have also a very big market with respect to consumer electronics and other like signaling. So a lot of other things. One, what I consider to be an important application are active light emitting clothing. So for example, when you have workers at night on the streets, that you have something that not when you drive up with a car where reflections comes up and you see there's a person, but you actively are illuminated and give a signal even to those that don't have or wouldn't see you otherwise. And here we have the OLEDs. They're still very expensive to manufacture because you're injecting, like with the LED, the electrons and holes, and you have to make sure that they get transported to the light emitting layer and recombine there. And that's where you generate the photons. You have to give a lot of thought to the thickness of the individual layers and so on. And then 25 years ago, another concept had been put forward, and that was that of light emitting electrochemical cells, where you take simply a cathode and an anode on a substrate and put in between a light emitting layer. And the light emitting layer, that's where ionic liquids, again, just to close the cycle, come into play. Because in order to avoid this multi-stack architecture that you see on the left side of the slide, you now just take something that contains cations and anions, and when you apply a bias, they migrate in the applied field, create electric double layers on the respective electrodes, and you generate the potential drop that otherwise gets created through the individual layers just by the ion distribution. It's very simple. And you just need a light emissive electrolyte, an ionic liquid. And that's why we now engaged in the synthesis of metal-containing ionic liquids, where the cation, in this case here, the iridium cation, sends out light. Basically, you play around with the HOMO and LUMO of your charge transition metal complex, and like in an LED, you oxidize and reduce it. So you inject electrons and holes, they migrate through electron transfer now, and in the emissive zone, the light gets emitted. You have to play now with the valence orbital structure of your complex to get the HOMO and LUMO, so the energy gap, into either the blue, the green, or the red light emission. And that you can do by playing around with the ligands. So we're back to organic chemistry. But by that, you really, and that's just an overview slide of recent work we've done where we made those iridium complexes. Down there, you see some light-emitting electrochemical cells showing the light emission in the 3 basic colors. With that, I want to conclude, and I hope with this journey, I have been able to show you that ionic liquids really have a big potential, and that we can use them as a synthesis medium, as a reaction partner. We can use them for nanoparticles to determine which size the particles have, morphology, in which crystalline phase. But we also can use them as ion transporting materials and soft hybrid materials. Of course, this research would not have been possible without the people doing the research in the lab, and also the funding agency. So starting much of the initial fluoride work was funded by the European Research Council. We had a Marie Curie project that also sponsored the light-emitting electrochemical cells, but much of that also was sponsored by the Department of Energy in the US, and currently is sponsored at Stockholm by the Swedish Energy Ministry, Energimyndigheten. Again, I would like to thank the whole team that has worked in that. Many of them are listening in, and I hope that I gave you some really nice examples that maybe get you also excited, and that I brightened up a little bit the afternoon. And I'm happy to take questions.
Yeah, thank you, Anja, for this very enlightening talk regarding using ionic liquids for energy applications, in particular here lighting. I have several questions. Please, for the audience, just please post your questions in the Q&A section. And maybe we can start the Q&A directly. Anja, my first question is regarding ionic liquids and tuning crystal morphology and electronic properties. Is it actually possible to tune the P and N type behavior of semiconductors by differing the ionic liquids for synthesis? Because this is kind of a big problem in photochemical applications or in thermoelectrics, for example.
So you can,
in some cases, if it's possible.
Only in, I mean, all I know, and that kind of comes from our experience from that we've made through the both the photocatalysts and the thermoelectric work. You can tune the doping degrees. But like you're more referring to playing around with the surface.
Yeah.
Or yeah. No, we haven't. That's an interesting thought. No, we haven't looked at that.
One more question, Anja. If you synthesize these compounds with ionic liquids, do you make a hydrothermal synthesis, or is it just, how can we imagine this to be done? So you mix the ionic liquids with the precursors, and do you heat it up in an autoclave, or is it like an open reaction?
So reactions, so you can put it in a just sealed glass tube and put that in the microwave. So microwave reactions is what we prefer. You can also use the oil bath, but quite often when you want to make nanoparticles, you really want to have fast reaction rates. The other thing is you can simply use an ultrasound cleaning bath and put your glass vial into the ultrasound cleaning bath, and just that irradiation with ultrasound lead to the reaction.
Okay, good. Thank you. Shubik has a question. Shubik, please.
Yeah, Anja, thank you very much for a very inspiring lecture on the topic of ionic liquids. I learned a lot. And that, of course, raised several questions. Yeah, I have two naive questions. Yeah, please consider me as a bachelor student in this topic, or even lower. So
for that, I know your research too well.
So my first question is, if we use ionic liquids for photocatalysis, do you think we can also change the band gap of semiconducting materials? This is my first question. And my second question, I know ionic liquids, they have been used for CO2 chemistry in organic synthesis. Can you give us a bit hints like how it can be also applied for general organic synthesis? So normally in carbon dioxide chemistry, people believe that ionic liquids can activate CO2. So how it can be also applied for general organic synthesis, except the stability of the nanoparticles? Or have you seen some inferences in that area?
So now you're thinking of, for the CO2 activation, that you have an ionic liquid that absorbs the CO2, of course, and then influences the electronic structure in a way to activate it. Or that's kind of the way you're thinking, and then for the conversion of CO2 to whatever in the ionic liquid.
So normally the ionic liquids, the cation or the anion, I mean, depending on which one you are using, so they are also kind of known that it can activate the CO2 molecule. For say, I have seen a couple of articles that ionic liquids only has been used that kind of as a solvent as well as kind of a catalyst. So we cannot claim catalyst, but you know that can facilitate reactions.
Right.
For say imidazolium, let's say a very simple structure. The imidazolium is a kind of a mother precursor of NHC carbons.
Right.
And NHC carbons can activate CO2. It's very well known.
Right.
So therefore, also people believe that if we can take ionic liquids, then the two advantages. One is that you don't need any other solvent, so it can act as a solvent, and at the same time it can activate CO2 molecule.
Right.
So can we also utilize this kind of concept in general for organic synthesis?
I would believe so.
And what
I mean, there are some examples where also with, so where you see that, for, I mean, just taking aromatics and look at the relation of aromatics, that depending on the ionic liquids, you observe substitution on the organic core at different sites. And people say that this is exactly as you described the electronic, the modulation of the pi system by the surrounding ionic liquid. So that's what would come into my mind here.
Okay, I have a very quick second question, very quick. So do you also think that ionic liquid can modulate the band gap of semiconductor?
Yes, through the electrostatic interaction, yes.
So it's well known. I see. Okay, thank you.
Okay, I have also a question from Sehi Budnik from the audience. Thanks for a very interesting talk. Usually limited application of ionic liquids for industrial manufacturing is related to recovery or recycling issues, especially for the fluorine-containing ones. Which technology would you describe as the most promising in terms of environment-friendly recovery?
So here, like, if I take the example of the BF4 ionic liquid, where we added the metal acetate. So you run the reaction and you destroy the BF4, and the acetate becomes part of your ionic liquid. So it substitutes the BF4 anion, and you can run the reaction until you have consumed your ionic liquid. That's of course not the recycling, but since it's a reaction partner, you consume it. And then going back to the question, that was the recycling.
Yeah.
Oh. I mean, that really depends on the application. I've seen people recycling ionic liquids, and they spend so much organic volatile solvents on the recycling that it's crazy. But I know also from colleagues that are working with ionic liquids, for example, at BASF, that for some processes, they don't have the requirements of a really pure ionic liquids, and they can live with high degrees of, or higher degrees of contaminations. So I think it's not really that this is a showstopper.
Okay, good. Thank you for your answer. Robert had also a question. So I saw it, or am I wrong?
Yes, I have a question, but first of all, I wanted to say that a question in the chat slipped our attention, but this is already answered now. So maybe we move forward with the Q&A. So I can ask my question also after the lecture.
Okay, there's one question. It's very interesting to use ionic liquids for energy lighting applications. Ionic liquids are quite expensive. Is there kind of work going on to make ionic liquid synthesis easier if we compare it with deep eutectic solvents?
Yes, so deep eutectics and ionic liquids, they have different sets of properties. And historically, the ionic liquids that caught attention are based on the perfluorinated anions, which are always very expensive. They're known from battery electrolytes. You make them through electrofluorination. They're not green, they're expensive. Deep eutectics, we think of choline, chloride, and urea, two dirt cheap chemicals that combine and you get a deep eutectic. But you can equally well make ionic liquids from the natural pool based on the choline cation. So they, for example, choline acetate, so they do not have to be expensive, or oxalates. So we can make ionic liquids that are cheap and that are green, even FDA approved. You can eat them. And I think it's the same as with polymers. Historically, so I read an article about the development of polymers when bakelite came out, that people believed that this material would only be used by the upper class because it was so expensive and it was so expensive to make. And now we see polymers all around us. So I believe the demand in the end will make the materials cheaper. But I would not use fluorinated ionic liquids.
Yes. Okay, good. Thank you. I think, we have at this moment maybe not more questions, so we can probably continue then, and we can maybe come at the end of our lecture series to maybe more questions then. Okay, Anja.
Thank you all.
I thank you very much again for your participation in this great talk. Yeah, and thank you for supporting us here. Thanks. Yeah. And with this, I would hand the word over to Shubik.
Yeah, thank you, Adam. Thank you, Anja, for a great lecture. So now we move towards our second speaker, Professor Johan Martens, and it's my great pleasure to introduce Johan in this conference or symposium. So when I read actually first time Johan's CV, so I was pretty much very intrigued to read the whole CV because it's so enthusiastic, so inspiring. But then I realized that if I'm gonna do that, then 45 minutes is over. So Johan probably will not have any time for the things. So therefore, I need to shorten the CV. So he has received his PhD from the University of Leuven in 1985. Followed by that, he did habilitation and finished in 1988. Thereafter, he joined as a research associate and became research director in 1996. And since 1997, he is the professor in the Faculty of Bioscience at the University of Leuven. Johan has published more than 500 articles and he has 85 patents. Additionally, Johan is the founder of 4 spin-off companies and the 5th one is under progress, which is super impressive. So there is no doubt that he has won numerous awards. So some of them I'm gonna mention as I already mentioned it. He has received Exxon Chemical Biannual European Science and Engineering Award for pioneering research in heterogeneous catalysis for hydrocarbon and natural feedstocks. He became the Belgian Franke Chair at the University of Antwerp. He is the laureate of the Enterprise 2005. He's the recipient of Methusalem funding, which is the highest level of structural funding for individual researcher in Flanders in Belgium. He has received Febelic Energy Award in 2015. He became the fellow of the European Academy of Sciences since 2017. And he has received ERC Advanced Research Grant in 2019, which is super prestigious. So with this, Johan, I am very much looking forward for your inspiring chemistry in the development of green hydrogen. So stage is yours.
Thank you, Jubik. I'll try to share my screen. I hope it works.
Yeah, we can see it.
You can see it. And then I open the screen. Voila. Yeah, thank you for the introduction. Yes, it seems impressive, but it's not that impressive. There's lots of work to do still. And yeah, I'm starting with this picture because I like it. It's in Brussels. It's a picture of the building of the Academy of Sciences, where people meet and discuss. It started 200 years ago, and still today it's a locus. It's kind of an island of silence where you can still work and reflect on things. And that's actually the place where I started to think about hydrogen. So this research we started 15 years ago. And I was thinking, in those days, hydrogen was not that important. And so I was reflecting on with colleagues on hydrogen and how to make it, how to store it, how to transport it. And that's the story I will be telling today. And 15 years later, I think I can show this picture. In my opinion, and in the opinion of many people, the future is just around the corner, and the future in the area of energy, that's hydrogen. Let's see why we think so. Hydrogen, well, there's green hydrogen. Today you have all kinds of colors of hydrogen, although hydrogen doesn't have any color, but there's green, there's gray, there's even purple, blue hydrogen, etc. So no matter the color of the hydrogen, we will come back to that, but there are many applications upcoming, especially in mobility. So there are cars, hydrogen cars, buses, trucks, trains. There are even airplanes powered with hydrogen. There is logistics, tractors. There are in the homes for heating, for generating the electricity, for storing energy in buildings, and industrial production, in the chemistry of the future, in sustainable chemistry we are talking about in this lecture series. Hydrogen will play a very important role. And I try to summarize it in this scheme. The chemical route to a CO2 neutral world is a paper we've written in 2017, and I think it's still valid today, and I hope I believe it will remain valid for many years to come. So what is the story? You can make hydrogen well, many ways, and you will use it to deal with the carbon. CO2, and that's in fact the story of our planet. 5 billion years ago, we had an atmosphere that was full of carbon dioxide, and it was the photosynthesis that transformed all that carbon dioxide into the atmospheric air we know today, with lots of oxygen and nitrogen and only ppm levels of CO2. So photosynthesis has turned all this CO2 into plants, into biomass, and this then in the geological time frames was converted into fossil carbon reserves, which today and in the past century we have been mining extensively as oil, natural gas, coal, etc. We are refining this in our petroleum refinery installations. And then we are burning this carbon very fast. So that's milliseconds or even shorter, the time frame of a combustion process. If you compare that to the millions of years you need in the geological cycle, then you don't need to be a big engineer to understand that this cycle will not keep on turning, and that there is a timing problem. So what many colleagues propose is, well, let's just take a shortcut here, and we grow plants, algae, etc. And we use that biomass immediately in a biorefinery instead of a petroleum refinery, and make again fuels, make materials, make chemicals out of those biomasses. Now, the growing of biomass, what is the time frame? It's days, months, years. For wood, it's many years, etc. Again, on the time frame, it's if you burn that biomass for making for energy purposes, again the circle will not hold because the burning is much faster than the growing of the biomass. So you need something faster. What is faster? That's CCU, carbon capture and utilization, because that's chemistry, that's chemical reactions, which you can accelerate with catalysts. And so converting CO2 into the products we use as fuels and as materials and as chemicals, that's something you can do. But then you need hydrogen in order to convert all that CO2 into valuable products. So we will need lots of hydrogen in the future. And this is, there are two types of hydrogen. I will not talk about the colors now. There's other ways to introduce this hydrogen. It's the E hydrogen, which is produced with electricity, and the S hydrogen, which is the solar hydrogen. I've explained it here also on the left lower part of my slide. Made from green electricity, you get the E hydrogen, and made directly from sunlight, you get the S hydrogen. E hydrogen, that's something which is already existing. It's typically applied for the electricity production peak shaving, when you get excess electricity production, when there's a lot of wind or solar irradiation. You can use that excess and convert it into hydrogen with electrolyzers, so wind turbines or solar plants combined with electrolyzers and store that hydrogen. That's a way of coping with this excess electricity production. Today there are thoughts about doing this massively offshore. This is something I took from a website of Tractable, where they propose to have windmills, wind turbines offshore, and use that electricity in a converter platform, either to feed electrical grid on land, or to feed electrolyzers on land. But more and more people are thinking, instead of installing cables, electricity cables, that it would be more economically favorable to do the electrolysis offshore and install electrolysis plants, electrolyzers on platforms, on sea, even use that hydrogen to do hydrogenation reactions and to create liquid organic hydrogen carriers. That's a nice word for saying organic molecules, which you can dehydrogenate when they are transported by ship to harbors, and thereby dehydrogenation, you can liberate again the hydrogen. These are ideas that are around. There are already applications like this, and there are more and more coming. So that's the e-hydrogen story today. It's a pity with all our pictures here, we don't see at the left of the screen, maybe you see it, there is a picture of a hydrogen generating factory in the middle of the sea. I hope you can see that on that screen. Now, we need something like 18 terawatt energy to power the world. Where could that come from? If we would use all agricultural area and grow energy crops, that would be 7 terawatt, so it's not enough. Hydropower, another 7 terawatt. It's not enough. Tidal energy could account for 14. Geothermal, also something in the same range. Then wind power, that's already more. It's something like in the 70s. But then solar, that's huge compared to all other sources of energy. So that will be largely sufficient. So we should use more sunlight for powering our world. That's the source, which is plenty available. So, yeah, that's my dream. We mount a valve on the sun, and the hydrogen is just tapped from the sun. Is it realistic? No, of course. This is just a picture. We cannot mount a valve on the sun. The sun is plenty of hydrogen, but we should do it another way. And the two ways you could do this are the photocatalytic route, and Anja touched a bit on photocatalysis for water splitting. Now, this is a technology that's still quite in its infancy. I'm sorry to say so, but the efficiencies, solar to chemical energy, are still low, something like less than 1%. There's another approach which is already more advanced. That's the photoelectrochemical system, photoelectrochemical, that's using semiconductors and generating holes, electron hole pairs, and using them directly with catalysts in order to split the water molecule into oxygen and hydrogen. I've indicated here TRL levels. What is technology readiness level? Well, what is level 0? That is when you get a good idea. Just you wake up at night and suddenly you have an idea. That's TRL 0. It's just something in your mind. TRL 1 is when it's demonstrated at small scale in a laboratory. And the TRL level, it goes up to 9. That is when a technology is really on the market and is applied at a large scale. So photoelectrochemical is already more advanced. It's TRL 5, which means there are systems outside in the real world, in the real conditions for applications, prototypes that have been or that are being evaluated in order to come to something that's to production of semi-commercial materials. Then you climb the TRL level 6, 7, 8. That's 8 is already prototypes with, let's say, a serious, some limited serious production, and then 9, of course, is a full production. So these photoelectrochemical devices, I've put 2 slides of examples. They work pretty well. This one here is a publication of 2018. 19% efficiency solar to hydrogen, which is quite good. A solar panel does something similar, about 20% efficiency solar to electricity. So it's about the same efficiency. They do better than, for instance, what I was discussing before, the E-type hydrogen, because if you first, with these PV panels, you produce electricity with an efficiency of 20%, and then you have to convert that electricity into hydrogen with an electrolyzer, and that's only, for instance, 60% efficient, then at the end your overall efficiency is 12%. So if you get 19, it's pretty good, and it's certainly competitive with the E hydrogen production. So these are examples of the S hydrogen directly from sunlight over some monolithic electrochemical devices, making the 2 gases, the hydrogen and the oxygen. Some people propose very complicated things like this one. It's a stack of several semiconductors with multi-junctions in order to use effectively the whole solar spectrum and to maximize the generation of charge carriers, which are then used to split the water molecule into oxygen and hydrogen. There's a competition going on in the world for the best efficiency. Now, we thought we go in another direction. We also make PEC cells, photoelectrochemical cells, but we go not into the direction of winning the competition for highest efficiency. No, what we would like to do with our panels is to have something affordable, which can be produced in massive amounts without expensive elements, no noble metals, no exotic semiconductors, etc. And by working hard for 10 years, we succeeded to get panels. And here's a photograph with my co-workers. Very proud about this first panel. This was which was produced. And what does this panel do? It's shown here very schematically. It sucks the air, and from the air it absorbs water. So this panel doesn't need some water supply. It uses the water vapor that is contained in atmospheric air. So no water supply needed, no electricity supply needed. The energy comes from the sun. So the panel is illuminated with solar radiation. The water comes in as a vapor, and it's split internally into oxygen and hydrogen. That's what it does. And here are some figures. So we reach 15% efficiency at optimum conditions. So with perfect orientation, with the best combination of relative humidity, because in our case, it's not only the sunshine that matters, but also the relative humidity. It's a combination of the two. So the average, if you put it outside in Belgium, over a year time, all the seasons, winter, summer, autumn, spring, we get 11% average. So that means in Belgium, 6 kilograms of hydrogen produced for one panel, which measures 1.65 square meters. And of course, we make more oxygen because the oxygen atom is, of course, heavier than the hydrogen atom. You are all chemists. So that's simple. So many advantages, and that's what from day one we were targeting such a system that had these properties. So no liquids inside, it's black box, so you don't need to do anything. You put it outside, sun shines on it, it starts working. So it's solar hydrogen from sunlight and air. You can put one panel, and then you are in the kilowatt range. If you put thousands of them, you are at or 100,000 and more. So in fact, you could make parks of these panels and go to gigawatts. So it's safe because the hydrogen that is produced is at low pressure, slightly above atmospheric pressure, leak-free, predictable, because it's independent of external factors. You don't need an electricity supply. You don't need to a fresh water supply. So it's only microclimate dependent. And so we have models that simulate the functioning of the panel, the production of the hydrogen that goes up and down, up and down, up and down, a bit like a PV panel, but even more pronounced, because weather and especially microclimate, it changes quite significantly, especially in a country like Belgium. So affordable, as I mentioned already, no noble metals, no expensive compounds. So this is the famous graph of reported solar to hydrogen efficiencies on the y-axis, and here on the x-axis, the light absorber size. So our panel measures 16,000 square centimeter. Many people in the world are producing and are reporting photoelectrochemical systems with excellent efficiencies. You see, it goes up to 30% efficient. But now most of these studies are done at small scale, at the centimeter scale, even the millimeter scale. That's, of course, if you use such a very complicated stacks with multi-junctions of semiconductors, it's difficult to scale up to the meter scale. And so we are here with our solid solar hydrogen project. We are in the upper corner at the size which is ready to be used in practical applications. If you compare, for instance, wind turbines plus electrolysis with solar hydrogen panels, you see this is the estimate of hydrogen you can produce. Well, on the same area on land, and the red spots are the places where you have the wind turbines. For instance, you have the 4 wind turbines here. If you would use the same area and put hydrogen panels on that area, you would have a production which is 3 times higher for hydrogen, solar hydrogen, than for e-hydrogen, which you would then produce with electrolyzers that are converting the electricity produced with the wind turbine. So there's really the shortcut from sun immediately to hydrogen instead of the detour via electricity and then electrolysis. It pays off. You could really get much more efficient systems as shown by these figures. Now, something about water, yeah, because, well, we should not solve one problem and leave another problem unsolved. In Europe, we are facing a problem of drought, and it's really scary. This is the prediction, and there are many models, but there's one particular model we are using here. So the drought severity index, the more red, you may recognize here the world, the map of the world, the more red, the worse, the drier the climate. And in the year 2099, probably I will no longer be around, but some of you may still be. Look how red Europe is coloring. It's Spain, and it's not limited to Spain or the south of Europe. Belgium is somewhere there. It's even England, historically known to be the wettest country in the world. Well, there will be a drought problem if the climate change continues as it is doing today. And even Europe will be drier than Africa. So what is happening today? There's a migration of people from Asia, the Middle East, and Africa to Europe. But in fact, they are joining a region where there's a shortage of water. What can you do then? Well, that's we have been thinking about that. You could try to capture the water vapor from the atmosphere, absorb it, and use that water to generate hydrogen instead of entering into competition with other users of water, of fresh water, which is agriculture, which are the households, which is the industry, etc. So if you get it from the air, there exists technology to produce water from air. The things that are done today are summarized here on this graph, and you get also the energy that is required to produce a cubic meter of water. So the most of the water sources and the water production is, of course, ground and surface water. That's 0.2 kilowatt hours per cubic meter. Seawater desalination is much more energy costly. It's 4 kilowatt hours per square meter. Many colleagues are looking for adsorbents, desiccants, that can absorb water from air, absorb or adsorb. Some ionic liquids could also do this. But then you have a problem because the water, if you have a good adsorbent, it means the physical adsorption energy is so high that if you need to desorb the water again in order to produce it, you need lots of energy. And you see 1,400 kilowatt hours per cubic meter. That's because you need to absorb, that's exothermic. You need to desorb, that's endothermic. You need to condense again in order to get liquid water. So this is really a process that is very costly for energy. What we do in our panels is, in fact, we catch the water and split it immediately. We have no phase transitions of the water in our panel. The vapor, it's all vapor phase inside. So this vapor, the water vapor, is immediately split into hydrogen and oxygen. So this 0 kilowatt hours for handling water in such a panel. Right, so this is a bit our future, how we see the future. It's the map of Flanders, but it's representative for Europe. You can have the same picture in Germany, in Netherlands, France, etc. So in the future, we will need a lot of hydrogen, and it will be either e-hydrogen that is produced offshore, or that is imported from other continents where it is produced at places where there's much more sunlight or wind. That's one source, and that will be used especially for the chemical industry, which in Belgium is located especially around Antwerp, Ghent. Here at this place on the map. And then we see opportunities for the S hydrogen onshore, like with our panels, but there may be colleagues coming up with similar things, which then is a third source of hydrogen, which you could produce at many places. For instance, the combination with agriculture could be interesting. We have lots of problems here, for instance, in Flanders with crops, and especially in springtime, that you get frost at night and the blossoms can be frozen. And for instance, for apple and pear production, this is dramatic. Well, you could think of kind of covers of hydrogen panels, which may have multiple functions, not only produce hydrogen, but you could also protect the crops from extreme weather conditions. You could mount it on homes like here. So here are hydrogen panels next to PV panels, and then you get a combination of fuel, the hydrogen, and electricity, and you can, depending on the demand, combine the two. So many possibilities. Good, that's one aspect. That's the production of hydrogen, and I try to convince you that solar hydrogen, the photoelectrochemical approach, is something worth developing more, and I believe we will see it sooner or later in the streets, in the landscape, these panels. Another thing in the hydrogen economy is the storage and transportation of hydrogen. It can be done via pipelines, that's one. It can also be done with cylinders, and there today it's really dramatic. The energy expenses of storing and transporting hydrogen these ways. For small scale, you have compressed cylinders. The pressures in those cylinders, it's 200 bars, 300 bars. For the tanks of trucks and cars, it goes higher. In cars, it goes even to 700 atmospheres. So very high pressures are needed to have a significant content of hydrogen in these tanks. The medium scale and the larger scale typically it's liquefied hydrogen, and the liquefaction of hydrogen that's done at very low temperatures. You need minus 253 degrees C. So that's even more energy demanding. You lose something like 40% of the energy that is contained in the stored vessel by simply the request for cooling that deeply. Ships are being constructed for transporting liquid hydrogen, but there's really a gap in the technology today. Some things, storage system that is more efficient than compression and liquefaction. Well, there are some alternatives around. So on this figure, you have on the y-axis volumetric capacity, grams of hydrogen per liter storage tank. And on the x-axis, the gravimetric capacity, which is the weight percent hydrogen. Now, these are small numbers, 1, 2, 3, 4, 5 weight percent. For instance, for empty tanks, why are the capacity so small? Because you need to withstand the high pressures. You need a lot of steel or complicated materials that withstand the pressure. So 350 bars, 700 bars, you see the spots indicating the gravimetric capacity 5, 6, 7%, and the volumetric capacity like 20 up to 30 grams of hydrogen per liter. The metal hydrides, they do a bit better volumetrically, but of course the metal contributes a lot of weight, so that diminishes the gravimetric capacity. The metal organic frameworks are a bit better gravimetrically, but volumetrically a bit similar. The LOHCs, I talked about it at the beginning of my lecture when I was talking about offshore hydrogen production, hydrogenation of organic molecules, and dehydrogenation at the spot where the hydrogen is needed. So this is an example of such a chemistry, an emerging technology, the liquid organic hydrogen carriers. One of the candidate molecules is this dibenzyl toluene molecule, which with hydrogen from electrolysis you could hydrogenate. You need 9 hydrogen molecules. You need a catalytic process with platinum, etc., in order to hydrogenate all the aromatic rings. And then you transport this per hydrogenated molecule. It's a liquid, so you can use the technology that is existing today for transporting diesel or petroleum products, etc. And then at the spot where you need this hydrogen, you need another plant, a catalytic process, again platinum, to dehydrogenate the molecules and regenerate the aromatic molecule that can be sent back to the site of production of the hydrogen. Is this a good technology? It may be, but still we are using here molecules, organic molecules, which there may be side products. Yeah, you may have cracking, hydrogenolysis of these molecules. You may make VOCs with leakage. Well, these are aromatic molecules, not so nice for the environment, etc., etc. I know there are big projects like in Germany and some demo plants also in Finland, but I don't think this will be the ultimate technology. What I believe that we should do is to store the hydrogen in ice. Ice, solid water, is lighter, is less dense than liquid water. It's an exception, in fact, that the solid, an iceberg, is floating on water. Why is this? That's because it is porous. And ice is one example. In general, one could speak about clatrate hydrates, which are small capsules of water molecules that are bound via hydrogen bonding, in which you can store molecules. The best known clatrate hydrates are the methane ice. You can also store CO2 in that kind of structures. Hydrogen is a difficult one. And if in the bulk, if you would like to store hydrogen in a clatrate, you would need 2000 bar or very low temperature, so it would be very impractical. We discovered a way to do this, and it's using these blue features in a tank. And with these blue features, you can make hydrogen clatrates at very attractive temperatures and pressures like -12 degrees and 60 bar. What is this magic blue thing? Well, that's hydrophobic material, hydrophobic matrix material. And why hydrophobic? Well, in hydrophobic environment, water tries to find other partners for binding. It is reorienting the hydrogen and the oxygen atoms, and that hydrophobic environment, it favors the formation of clatrates. And it's really spectacular how these clatrates form so easily when you simply pressurize such tank. You fill it with liquid water, you cool, you introduce hydrogen pressure, and you get your hydrogen clatrates. And then loading and unloading is very simple. You pressurize and but because once the clatrate is formed, that's something I should mention. Once the clatrate is there, it stays there. You can empty and fill the clatrate structure at will. So you even don't need to recrystallize it again. It's there, and you can empty and fill it at will with hydrogen. That's something spectacular. And the potential is tremendous. There exist many artificial clatrate hydrate structures. The most popular one is structure 1. It has 2 types of cages. You see the structures on the slide. And in each of these cages, you can have 1, 2, up to 4 hydrogen molecules. The density of hydrogen molecules in such a structure is almost similar to liquefied hydrogen. So you can store the same amount of hydrogen in a liter of a clatrate than in a liter of liquid hydrogen in an empty vessel. The difference is that you don't need minus 253 degrees C. You can do this at minus 10, even less. And this is the potential of clatrates, different structure types that have been described in literature. So S1, S2, the old structure types. Look at the values. It goes up. The structure 6 goes to 7.2 weight% hydrogen. Ice structure 1C, it can contain up to 10 weight% hydrogen. And if we put this on the graph I've been showing in the with all existing technologies at the start, a few slides back, well, in green you get the arrow of the potential of the clatrates. See how far it goes with structure 6 as with the Roman figure 6. You are in the range of cryo-compressed hydrogen. If you would make the ice structure, you would be far better gravimetrically as well as volumetrically for storing hydrogen. I think that's the future. Today we are compressing at 200 up to 700 bars or cooling at minus 253 degrees C. I think in the future, well, you will get hydrogen from the freezer and you can store hydrogen easily. Well, this is of course a bit a joke. There will be very simple technical solutions. So we will be driving a hydrogen car with the tank cooled at minus 5 degrees C, and you could drive from Belgium, for instance, to the south of France without having to refuel because of the high energy density that you would create. Good, so we have a very nice consortium in Belgium working on these artificial clatrates with colleagues, a lot of colleagues from Antwerp, Sarah Bals, Jo Verbeek, who are looking in electron microscopy, Cryothem, they're looking at the structures of those clatrates. Peggy Cole is contributing hydrophobic materials for as a catalyst to nucleate and grow clatrate phases. We have Patrice Perrault, Sami Verbrugge, and Sylvia Leenaerts, who are also in Antwerp. They are looking at the development of processes based on clatrates, together with Yuri De Nayer at the University of Brussels. We have molecular modeling. Veronique van Spijbroek, modeling the clatrates, also the diffusion of hydrogen in clatrates, etc. Pascal van der Voort. He is doing he's also developing host materials for hosting the clatrates inside. Good, I think, well, this is the team. That's our hydrogen team, solar hydrogen team. And we are about 10 people in the lab working on the solar hydrogen, and on the clatrate team we are 3. So it's quite important part of my lab working on the hydrogen technologies. And see, this is a slide I showed at the beginning. The future is just around the corner. And I put a question for you. Do you agree based on what I've been talking? I hope I didn't talk too long. And I'm looking forward to discuss about this and to learn about your opinion about these ideas. Thank you for listening.
Yeah, Johan, thank you very much for this very inspiring chemistry, very inspiring lecture. So initially I was not agreed, but now after listening your talk, I agree. Definitely. No, it was very convincing and very nice topic. So of course I have plenty of questions. So, okay, let's first ask that. So I saw you have also talked about LOHC, and you know I'm organic chemist, so obviously it took my attention. LOHC is good. The main issue, I mean, my personal point of view is that the dehydrogenation, because the temperature is quite high, fast. Second is, you need particularly an heteroatom to make it a bit atmospheric pressure or lower temperature. So
yeah,
in that sense, how is the dehydrogenation procedure for clathrate?
yeah, you're absolutely right. Clathrates, so the first time you make a clathrate, that's a difficult step. But once you have the clathrate structure, we were very surprised that you can empty and fill the cages without destroying the clathrate structure.
Okay.
And so if we would have to crystallize again, if it would melt and recrystallize, melt and recrystallize, we would also have, I think, a complicated process, a very difficult process. But we are surprised to find that you don't need to do that. Such a clathrate structure, if you stabilize it in a hydrophobic, and I emphasize on hydrophobic, in a hydrophobic environment, in nanopores which are hydrophobic, then it's much stabilized. So this hydrophobic environment, it exerts a pseudo pressure on that phase, and that keeps it stable. And that's amazing, the gains you generate by hydrophobic. That's also the topic of my ERC advanced grant. It's the behavior of water in hydrophobic pores. And that's really unexplored, an unexplored field. So you need to pressurize to have the water inside, and you need an intrusion of the water. But once it is inside, it does the chemistry changes completely. For instance, the acid constant, it changes completely. It becomes more aggressive, this water, depending on the environment, depending on what you do with it. In some pores, you can generate water that resembles supercritical water even. In other pores, well, here we don't need this supercritical water, but we start to get a handle on water. Well, there's in Germany, there's a new center created, the Center for Molecular Water Studies in Hamburg. Maybe the colleagues may know this. We are the NMR hub of that center. That's really, well, it's an unexplored field, and it would be nice that more people join, because there's lots to discover about water. Water upon confinement in a small pore. That's really, you can't compare it anymore with normal water. You can turn water into acetone. The dielectric constant of water is 80. If you confine it in a pore, it may go down to 20, and that's like acetone. So, and then you can, for instance, dissolve much more gases, much more organic molecules in it. And that's why it works for making clathrates.
Yeah, thank you, Johan.
You're welcome.
I see my colleagues have questions. So Adam is already ready to ask the question.
Oh, yeah, sure. So I will just go. Yeah, thank you, Johan, for this very nice talk and very interesting ways to store hydrogen. I wanted to ask you about your opinion about storing hydrogen in ammonia, actually. I mean, this research has been kind of been done since the 50s, also with the hydrazine, the motorbike, maybe you know this. And now it's this research on kind of oxidation of ammonia is coming up.
Yeah.
I wanted to ask your opinion, what you think about this technology for the future.
Yes, if you would put ammonia on the slide, well, I will not. So I showed the slide about the volumetric and gravimetric capacities. Ammonia is far up. It's something like 18 weight percent, because you have 3 hydrogen atoms for 1 nitrogen atom. Now ammonia, there remains a problem, that is the decomposition of ammonia. Decomposition, so the synthesis of ammonia, you have the Haber-Bosch process, and that's established chemistry, etc. You should electrify that process in order to make ammonia, green ammonia. That's one thing. And Haber-Bosch processes are huge plants. So in order to electrify those, we shouldn't do that in Europe, probably. We should then do that somewhere else in the world. But then if we ship the ammonia to Europe, what will we do? Will we decompose the ammonia to get hydrogen again? But that's the difficult. Chemically, it's not solved. there is no efficient process for decomposing the ammonia. I know Schorkendorf has shown that you can do it, but at a small scale. And for many applications of hydrogen, you should not have traces of ammonia left. Ammonia is really problematic in some catalytic processes. It's a poison for acid sites in catalysts. It's a ligand for metals. So ammonia is a nasty molecule, in my opinion, and it would be much better just to transport the hydrogen. Why? So an alternative is methanol. We would send our CO2 to Chile, and there they would make methanol and send the methanol back to us, and so that's then the energy carrier. I'm not fond of all those suggestions. Okay, if there is nothing better, fine. But I think latrates. So I would let's ship icebergs of hydrogen over the ocean. They even float naturally.
Yes. Okay, thank you very much for your opinion.
Yeah, Robert, please.
Right. Thanks also from my side for this very exciting talk. And I was really impressed by the solar hydrogen production panels. And you've shown that you can beat the combination of the photovoltaic cells in terms with electrolyzers in terms of efficiency. And I'm wondering whether you have already estimated the lifetime of your cells, and could you comment on that? And could you compare them to the conventional setups?
Yeah, of course, our project is not so old. So in order to estimate the lifetime, we can only extrapolate. We for instance, we have set one panel outside for one year, and based on the degradation we observe, we estimate that it's quite robust what we made. So certainly it will live 5 up to 10 years. It could be that from time to time you need to, well, that's the first generation only, but I'm quite confident that at the end we will have panels that are so robust that they can have a lifetime of 20 years. So this, yeah. Because, well, maybe it may be puzzling why that is, but our panel works at the rhythm of the sun. And the energy density of sunlight is not that high. So that's why the components in the panel do not suffer that much. In an electrolyzer, you get amperes of current, and that's of course demanding for materials, for all the components, for corrosion, etc. But our things, they just need at the rhythm of the sun. Okay, and so that's, we have good efficiency, but still we have one sun, 1000 watts per square meter, that's it. And that's why it is so robust and so reliable.
And when it comes to the purity of the product, is there, can you say whether it's better or worse?
Well, today we are investigating together with a company that is responsible in Belgium for the natural gas grid. And we are investigating the injection of our hydrogen into the natural gas, into the methane, because you could have quite a substantial percentage of hydrogen in the gas, in the methane, and still have no problems with burners with the application. If I'm not mistaken, you can go up to 40% without any problem. Our hydrogen, and so that's a project that is running now. We have 4 panels installed at an industrial site where they investigate the quality of gases, etc. So Flux is the name of that company. And so far we get our hydrogen. The only problem is that it is hydrated, and that should be not a surprise because we're making it in presence of absorbed water from the atmosphere. But besides that, the quality is exceptionally good. So it's 99.99 hydrogen. So very, very high. The only impurity is nitrogen. And after one night, the first hydrogen that is produced, that should be not should not be injected, because then at night you could have a little bit of impurities, that you get some oxygen, etc. Always up to now very small amounts, but so it could be that after one night, because it doesn't work at night we absorb the water from the air, and during daytime when the sun rises you start the splitting. So the first hydrogen you make, that's not the highest quality, but after 10 minutes or so the first production you should discard, and then you get a full day of nice hydrogen production. Yeah, it's I'm living on a cloud. This is for me in my scientific career really the most exciting moment, that we are living this wow, the success of the hydrogen panels. Something we are trying, and what we will do probably is also introduce it in the third world. So our panel would work best at the equator, where you have very humid conditions and plenty of sunlight the whole year round. So the productivity is 6 kilograms per square meter per year in Flanders. In Spain, it would already be 10 kilograms. And if you go more south, it goes up. For instance, one of the problems of the climate change is that a lot of wood is still used for cooking. 3 billion people on this planet are still using wood as their only energy source, burning wood, collecting wood, cutting forest, etc. If we would supply them with such panels, and that they can have cooking stoves based on hydrogen, that would also be something that is really worthwhile for saving the planet, for countering the climate change. So where shall we start? That's for us now the big the big problem, to make good choices and to select the right application fields.
Yeah, Johan, thank you very much. Thank you very much. Now I guess it's not only me, I guess all the listeners will agree with you that green hydrogen is the finest solution for the future. However, we have some general question. Normally we do raise to our speakers. So today actually we have picked up, like, how do you motivate your students in the lab? Of course, it's a beautiful project, so that part is gone. But when, let's say, some sudden breakout or something, how do you motivate your students first? And second is, what will be your advice to the upcoming students, PhD students, those who want to join PhD?
How to motivate students? Well, we should just, the way I was talking today, that's the way I'm talking to students. Okay. And yeah, I get plenty of applications of students who would like to make the PhD and join this project. I think the message is, try to be creative and try to be original, and don't follow the hypes. And at the beginning it's difficult. When we started these projects, nobody was doing this, so we were really, it was difficult to get things published even, because we sent the paper and the referees didn't understand what we were talking about, and we get silly comments. Yeah, it was frustrating for my students at the beginning. So yeah, but what are we doing here? No, our first panel had a miserable low performance, 0.1% efficiency. They said, "Wow, we stop." I said, "No, let's continue." And yeah, once the success is there, it's easy. But I can assure you, in the first days. So another project I'm doing today is trapping water from the air for having water, being faced with drought in Europe in the future. So can we just capture the water vapor from the air for having water, for producing water? It's not an easy job. You can of course do adsorption and then release the water, desorption, etc. But that's much too much energy demanding. You need clever ways to do that, and there are clever ways. And maybe ionic liquids could do something to trap water and release water again. I don't know, Anja, whether there are thoughts in that direction, but with salts, with super absorbers, but you need to find, there are those thermoresponsive polymers, which they are hydrophilic low temperatures, and once you start heating them, they become hydrophobic, and there's liquid water seeping out of those polymers. That's quite impressive, that technology, and nobody is looking to use it for this application. It's being used in biomedical applications, etc. But it's curious. Well, I think we should come up with, that's why I consider it as convergent research. Let's try to face all the problems and not just one problem. I'm sure everyone can contribute also to the COVID-19 problem, not only the virologues and the biomedical people. Yeah, there also you could do things, but don't hesitate. Tell your students and tell them, be creative, try things, and don't go the easy way. We need you to save the planet.
Yeah, I mean, thanks, Johan, that you already made Anja to switch on her camera. So the same question, so the same question I have with Anja. Anja, how do you motivate your students in the lab? And second question is, what will be your advice to the upcoming PhD or postdocs to stay in academia?
I think I always find it, I mean, motivating. One can try to be a role model. One can try, like when you did it, it's you present, one can really feel how engaged you are, and the spirit transpires, and all the fascination. And I believe, when I think back, why did I stay in academia or became what I was? It was, you find something interesting, and it was not so much that I felt that somebody else worked hard to motivate me. It was just, I was looking around and I felt inspired by other people, by people around me. And that's probably something that I also like, where I would like to give students and co-workers a creative space where they can develop. I mean, it's sometimes, I always felt my supervision technique is not to, it's more to trust into people, and to give them the possibilities, the infrastructure, everything to become their own, develop their own ideas, than to press them into a topic. And I think that that's always the freedom I love in academia, in contrast to working for industry, where you have a project, you have the milestone. I mean, I worked for quite some time for the Department of Energy, and what I absolutely hated were projects with milestones and road mapping. Because it takes so much away from creativity.
Sure. I mean, I also worked in the industry, in pharmaceutical industry, in GSK. So, I mean, those who have worked, I guess Johan has several industrial projects. So obviously that also creates the same roadmap and same target and target-oriented research. We all agree that in academia, we have that liberty, and that we like to enjoy that liberty behind this creative skill.
Yes, but if I may, the climate is changing, also in academia. And if we look to European projects, it's all about milestones, work packages, and you need
except
to
for ERC.
ERC is dramatic. You buy a pencil and you should justify what you will do with that pencil.
Not for the ERC, though.
Oh,
I mean,
yes. The audits for the ERC are getting worse.
Okay, then it has changed, because when I had mine, it was, as long as you could justify it, but they didn't count the pennies.
Yeah, well, researchers, we are evaluated every day. Every day we need to justify ourselves. We need to prove that we are busy, etc. And I don't know any profession where people are so motivated than in research, and still we are hunted, and people don't trust us, etc. If we would compare ourselves to politicians, I think I could know where the most serious people are working.
Yeah, but you're right. We are probably the most thoroughly evaluated people. And also, I guess we have to develop a very high frustration tolerance.
Yeah.
People only see the successful projects, but
Sure.
they don't see the rejected project proposals. They don't see the rejected papers and all this.
Yeah.
And that takes, I mean, sometimes, yeah, yeah, it's very tough to take that.
That's the bitter side of this academia.
Yeah.
But we always need to look at the positive side, that at least we can enjoy the creativity, and time is not, I would say, the blockage here. At least we can spend more time.
Mm-hmm.
That being said, so
I have one more question, Shubik.
please, Adam, please.
I wanted to ask both speakers to give us a hint in research. If you look at materials, the developments over the last year, the first criterion was the performance. We can kind of agree on this, probably with catalysts. What do you think where the next decade will go? Will the kind of sustainability be part or a bigger part in the performance analysis of materials, or will it stay like today? What do you think?
Anja?
So that when I talk to people in industry and my colleagues there, it is going to be more important. And particularly, we've been talking about circular economy, and I see that a number of companies are going in that way because they are also looking. I mean, economy is driving it, and circularity combined with sustainability and economy makes it powerful, and it also makes the design of new products, the development of new technological processes possible. So I believe this is doing a lot. And when you just look at, I mean, the re-regulation of the European Commission, so electronic waste, that has impacted so much developments in Europe and for European companies, but also from international players. So this is, I think, something we will see becoming more important in the next decade.
Yes, and the list of chemical elements for which we risk a shortage is growing. And that will be, if you propose a new technology with a chemical element which is critical, like the rare earth or whatever. Yeah, I think this should be considered from the start of a project, that you don't use or abuse Mother Nature. But that's for materials, but for any area of research, I think that we need to think about resources. Yeah, but sure.
Yeah, thank you for the advice. So it's worth doing sustainable research for the next 10 years and over this decade.
Yeah.
And if we as chemists and engineers don't do it, I mean, who should do it? So it's kind of on us.
Yeah.
Hopefully not the politicians.
But we have had many politicians, those who are enough to entertain us. We should not bring them back here, no?
Yeah.
Okay, that being said, so we are very much thankful to Johan and Anja for this very inspiring lectures and to educate us about the green hydrogen, ionic liquids. And with that, I would like to say thank you to both of you, and I wish you a very nice evening. So we hope to see you in, not in virtual mode, rather in a, in presence. That would be the ultimate target. Hope to see you soon.
Yes, having a beer together, that's something.
And that's what I'm missing.
I've
Good
been
Belgian
missing for,
beer.
The Quark.
I think me and Johan, we still can manage, and Adam and Anja still can manage, but we'll miss Robert. That's the point.
Yeah, I'm just in the middle of you.
we will manage.
Just in between you.
We'll manage.
Okay. Good, it's a deal. So thank you
again
and goodbye.
Yeah. Bye bye. Have a nice
Bye bye.
Goodbye.
You too.
Take care.